So for today, notes set, let's see, there we go. Notes set 15 is almost done. We've got most of the first page. You should have a little bit left on the bottom and then the back side. That's what we're going to finish up in this video. So flipping the camera here, all of this front and back here is on the kinetic molecular theory of gases. Kinetic molecular theory is what we're going to be abbreviating as KMT, kinetic molecular theory. Here are the assumptions that the kinetic molecular theory makes. Assumptions, and then we'll talk about them. On the back side, down here, for yours it's the back side, but I didn't print these double-sided. So my back side is here. These are the assumptions that are being made, and these are the explained behaviors that KMT addresses. So first off, excuse me, we're going to assume that gases, obviously kinetic molecular theory of gases, in a gas, the particles themselves are so small compared with the distances between them that we're going to assume, even though it's false, we're going to pretend, even though it's not real, that gases, the gas particles take up zero space. So it would be like, if this was a gas particle, and here was another one way over here, the size that they actually are is so tiny compared to the massive, whoops, not quite straight, but the massive amount of space between them that we're not actually worried with the size. And we're just going to say that they are just zero. They're just points. That's the first assumption. This is the reason that for many of your gas calculations, it doesn't matter what the identity of the gas is, because we're assuming that their size is zero. We're also going to assume, this is a big falsehood, but we're going to assume that the gas particles exert no forces on each other. AKA, we're making the assumption that there are no IMFs in a gas. Now, this isn't true, but these assumptions will help simplify the expected behaviors. We're going to assume that gas particles are in constant motion, bouncing all around, which is true. Collisions with the particles and the walls of the container is what causes pressure. That is true. And that the average kinetic energy, or energy of movement, is directly proportional to the temperature in Kelvin. What that's saying is that the more movement you have, that represents more temperature being in the system. So this is not true. This one is not true, but we're going to pretend that they are. All of these are the assumptions that we're making to, in order to idealize gases. The real universe is complete and utter chaos. There's exceptions to every rule. There's exceptions to every exception to the rule. But we're going to simplify it by trying to make this situation ideal. So by following these assumptions, these are the assumptions I'm operating under when I say that we're working with an ideal gas. You probably heard this in the last video and wondered like, what? Back when I was doing up here, I was like, this is the ideal gas law, PV equals nRT. It's just saying we are operating under these assumptions, which make the situation more ideal instead of realistic. Okay, so some of the behaviors that we can explain using KMT, this is the back side of the notes. We already know that pressure, volume, pressure, temperature, volume, temperature, and volume and the number of moles, all of these have relationships. What KMT does is kind of explain what those relationships are and why they work. So pressure and volume, assuming that the temperature is constant and not changing, pressure and volume have an inverse relationship. When the pressure goes up, that must mean that the volume was going down, or vice versa. If your volume got really large, then the pressure goes down. Think about this in terms of like if you are squishing a can of something. If you have an empty water bottle and you squish it, the volume is getting smaller, so the pressure inside is getting larger. They're inversely related. The next one, pressure and temperature, assuming that your volume is not changing. Pressure and temperature have a direct relationship because let's say that you have a temperature that's increasing. Increasing temperature means that there's more movement. The molecules are moving faster. They'll collide with the walls of the container more frequently, more forcefully, and that's literally the definition of pressure. Back here on our assumptions page, collisions with particles and walls of the container cause pressure. So when the movement is higher because the temperature is higher, the pressure will also be higher. That is a direct relationship. As the temperature cools down, we will not have as much pressure because there won't be as much collisions with the walls of the container. Volume and temperature also have a direct relationship. In order to maintain the pressure, the volume must increase proportionally as the temperature is increasing. So as volume increases, temperature increases, or they can both decrease. And lastly, the volume and the number of moles also have a direct relationship. This one makes sense. The more particles in a container you have, the more space is going to be required for that to happen. So most of these are direct relationships, more number of moles, more volume. The one that really trips up students a lot is the first one that was that inverse relationship, the inverse relationship between pressure and volume. If pressure is going up, volume is going to be going down, assuming that all of the other variables are not changing. So the next thing I want to talk about is particle speed and how the particles as a whole, what their speed is, and how that's affected by the different variables like molar mass or by the temperature of the sample. So the first one I want to address is, let's talk about, okay, first let's define effusion or effusion. And this is how they measure like the speed of a gas. Basically, you are measuring the movement of the gas through a small opening into an evacuated container. So you have an empty container with nothing in it, just empty space, absolutely no particles in it. It's a vacuum. It's not necessarily sucking like a vacuum cleaner. It's just a vacuum like outer space that has like nothing in it. Not even air, just literal nothing. And then it has a little hole. And what we're doing is we're watching how fast the gas particles go into this empty box. That's effusion. Okay, whew, sorry. My dog was barking and I paused the video and I don't know what I was saying, but I'm assuming I was talking about this. So effusion is the movement of gas going through. And what we're going to do to measure the speed here is we're going to measure it in this thing called the root mean square velocity. It's not like we're measuring the individual particle speeds. We're kind of measuring like the speeds as like a whole as they go through. So root mean squared velocity is going to be mean is average. And this is the formula for the root mean squared velocity. V is for velocity, and they usually distinguish this from other velocities like in physics by doing VRMS, the velocity, but the root mean squared velocity. VRMS formula equals the square root of 3RT over, and I want you to redraw this symbol. This is M, but it's the M for molar mass. And so when I draw it like handwritten, instead of having just M, it kind of looks like all the other M's that we have in chemistry, like molarity or whatever. So I put these little things on the bottom so that I know that this is the M for molar mass. So, molar mass. We're going to measure the molar mass in kilograms, which is kind of weird. We normally don't do that, but we need this to be in kilograms for our units to cancel out. I don't need you to understand why these cancel out, but joules, which is an energy unit, is dependent on kilograms. So we need kilograms for the molar mass. The R here, we've been using R equals 0.08206, but that's not the one that we want to use this time because we're dealing with velocities. We're dealing with the temperature in Kelvin. We're dealing with mass. And I told you something about joules, which you don't need to quite know. So the R value is actually going to be this one. This is the R that you use here. So let's practice a problem from the homework on root mean squared velocity. So homework 15 on the back side, it's actually homework 15B and kinetic molecular theory. On the back side is where we've got some calculations for the root mean squared velocity. So I'm just going to copy paste this formula from the notes, see if I can get everything on my paper at once. Root mean squared velocity equals 3RT over molar mass. V RMS equals the square root of 3RT T over the molar mass. We have to use the R that involves joules, which I find so easy to remember because it's like 8.31. And guess what? My birthday is 8/31. It's like August 31st. So super easy for me. But 8.31. The units don't super matter, but if you want their joules, joules per mole Kelvin. The temperature obviously needs to be in kelvins. So 25 degrees Celsius converted, what would that be? 25 plus 273, 298 kelvins. And this is our molar mass, but in kilograms. So normally, if we were doing nitrogen gas, nitrogen is one of the diatomic gases, have no fear of ice, cold beer. So there's nitrogen. Normally, the molar mass we would just say is 14 grams per mole. Or sorry, well, 14 for each. And then since there's two of them, it'd be 28 grams per mole for N2. But we need it in kilograms. There's 1,000 grams in a kilogram. So you can either do a whole dimensional analysis trunklet conversion or just move the decimal 3 places. So instead of having 28 grams per mole, we're going to have 0.028 kilograms per mole. Same, just converted. And I'm sick of using my husband's calculators, so I'm gonna, let's see. Ooh, I can actually make that really big. I'm gonna do this on Desmos here. So the VRMS equals the square root, okay, square root of 3 times R 8.31. It's my birthday. T for temperature we decided was 298 over the molar mass was 0.028. So I punch it in like this, and Desmos is telling me 515 right there. So that's going to be my answer for the root mean squared velocity. Whoop, my bad. So the root mean squared velocity of the nitrogen gas at 25 degrees Celsius would be, what did I say it was? I already forgot. 515 meters per second. That's how fast our sample is going. What happens to the VRMS speed if the temperature is raised to 50 degrees Celsius instead of just being 25? Okay. So assuming that everything else is staying the same, like the molar mass of the sample isn't changing, R isn't changing, 3 isn't changing, I pretty much am just comparing the square root of the temperatures, right? So on the one hand, from up here, from the first part, I have the square root of the 298 happening, and I'm trying to compare it with the speed of my new thing, which will be at 50. I'm gonna do this in, let's see, in orange, no. What color is good at contrasting? Light blue. So 50 degrees Celsius, that's, let's see, 50 plus 273, 323. So I'm actually going to put that one on top because that one's like the faster speed. 323 Kelvin divided by the speed of the other one, which was 298 Kelvin. There's nothing special about what I'm doing. I'm literally just making a fraction of the two speeds and knowing that it's going to be multiplied by this 515 original. I'm just seeing what the difference would be. And I think when you multiply it out, double check me, but I think this one you get 536 meters per second. You could do this a whole other way. You could literally just plug in the 50 and do it the other way, but just trying to shake things up. Part C of this sample is just to solidify for you, when do you use R of 8.31? The answer is when you're doing the root mean squared velocity calculations, versus when do you use R equals 0.08206? And the answer to that is when you have PV equals nRT. That's what this is here. You have a 5 mole sample of nitrogen gas in a 1 liter vessel at 300 Kelvin. Find the pressure of this sample. PV equals nRT. Find the pressure when the volume is 1 liter. You have 5 moles, 0.08206 is R, and the temperature is 300 Kelvin. Solving for pressure, you'll get an answer in atmospheres. Pervner requires this R. Root mean squared velocity uses my birthday, 8.31. Calculate the root mean squared velocity of a sample of oxygen O2 at 0 degrees Celsius. 0 degrees Celsius is 273 degrees, 273 kelvins. The VRMS formula is 3 RT over the molar mass in kilograms. O2 normally weighs, let's see, 16 each. So normally this would be 32 grams per mole. But since we need it in kilograms, I need to move that decimal 3 times. So I'm going to plug that in here. Plugging in 273. The R value is my birthday, 8.31. Plug that into your calculator to get the root mean squared velocity. I think it's like 450 something, but I don't remember. So there's the root mean squared. Next one, same thing, super easy. Root mean squared velocity of gaseous phosphoric acid. The hardest part of this problem is knowing what the formula for phosphoric acid is, so I'll help you out. If I ate the whole cake, I would feel icky. So if I had a phosphate that changed into phosphoric, a phosphate is PO4 with a 3- charge. So phosphoric acid must be PO4 with 3 hydrogens on the front. Phosphoric acid. Add up how much this weighs. Get your molar mass in kilograms. Plug it into the formula. V RMS equals 3 RT over the molar mass in kilograms. Make sure you use my birthday. Looking ahead at the next problems, like 9, it asks you questions like, how much faster is O2 diffusing than CO2? If they're both at the same conditions, same temperature, same pressure, how much faster would O2 diffuse than CO2, since like O2 weighs less? Yeah, weighs less than CO2. So it's going to be able to move a little bit faster. Or down here, a certain gas diffuses 5/3 faster. What is 5/3 faster? 5/3, whoops, 5/3 faster. So it's like 1.6 times faster than carbon dioxide. Which gas is it? This one, this one, this one, this one, this one, and we have to figure it out. So to do all of these, we're going to use Graham's law of effusion, and that's back in the notes. This is how we compare the effusion rates of gases. Graham's law of effusion is used to compare rates. The tricky thing about this formula is that the rate of gas 1, let me put this in yellow. I wish I had a highlighter, but I don't. The rate of gas 1 corresponds to this box down here. The rate of gas 2 corresponds with this one up here. The whole box is the formula, but we've got to like have it flipped. And sometimes with my dyslexia and stuff, it confuses me. But really, it's just this idea of like cross multiplying that makes it work. So keep this off to the side so you can use it on these numbers. So number 9, I'm going to copy, I'm literally going to move this paper. I'm going to copy this formula into number 9. I've got the rate of the first thing. Let's call the first thing the O2, the oxygen. Let's put the rate of the oxygen here. And then we'll put the rate of the CO2 on bottom. On this side, we'll have the square root of the molar mass that corresponds to CO2. And here we'll have the molar mass that corresponds to the O2. Matchy, matchy. O2 so it'll be cross multiplied correctly. CO2, so it'll be cross multiplied correctly. This whole, everything that I wrote is the formula. We're trying to determine how much faster oxygen will diffuse than CO2 if they're both at the same temperature and pressure. CO2 weighs, let's see, a carbon weighs 12. Each oxygen weighs 16. So CO2 weighs 44, but I could convert that to kilograms. I'll get there. The O2 weighs 32. So the square root of 0.044 over the square root of 0.032. So when I punch this in the calculator, I've got 0.044 divided by 0.032. I'm getting that this comparison is 1.172. 1.172. What that's saying is that the rate of oxygen compared to the rate of CO2 is 1.17. It actually rounds up to 3. 1.173. So the O2 will diffuse or effuse, whatever word you want to use, 1.173 times faster than CO2. Next one, oxygen has an effusion rate of 43.33 milliliters per minute at some temperature and pressure. Obviously, it's irrelevant. If an unknown gas at the same temperature and pressure effuses at a rate of 21.8 milliliters per minute, what is the molar mass of the unknown gas? So let me rewrite my formula coming from the notes, where it's got to be like, kind of zigzag cross multiply style. I've got, I wish I could keep all of this on my page at the same time. It's really difficult. Okay, the rate of, I'm comparing O2 to the rate of an unknown gas. So I'm going to use just a UNK for unknown equals the molar mass of the unknown cross multiplying over the molar mass of the oxygen. The rate of the oxygen it gave me in the problem. It said that the rate of the oxygen was 43.33 milliliters per minute. And the unknown gas is 21.80. I don't know the molar mass of the unknown gas, but I do know that the molar mass of oxygen is normally 32, but putting it into kilograms would be 0.032 kilograms per mole. Cross multiplying and dividing. Let's see, I've got 43.33 times the square root of 0.032, cross multiply and divide by 21.80. 0. And I'm getting, okay, my video cut out for a second here. But what I did to solve number 10, I think that's where my video cut out, is I plugged in the rates of comparison. I plugged in the 32 grams per mole is how much oxygen weighs. I converted it into kilograms. I got this number for the molar mass of the unknown. I had to square it though to get it out of the square root. But eventually when I did, I got that the final answer was 126 grams per mole. So oxygen, because it only weighs 32, can travel at a speed of 43. But the molecule that weighs 126 can only travel at a speed of 21.8. So I apologize if that's a repeat or my video glitched. I'm not sure what happened. And then I started on number 11 here, where it says that a gas diffuses 5/3 times faster than carbon dioxide. I added up the molar mass of carbon dioxide, and I kind of put it into this same comparison formula. 5/3 equals the square root of 44 over x. I'm solving for what that value is. So to solve this on the calculator, I'm going to cross multiply and divide. 3 times square root of 44 divided by 5. I got 3.97. And that 3.97, that's not the molar mass. That's the square root of the molar mass I'm looking for. So I need to square it, and I'm getting, okay, the molar mass now is about 16. It's 15.84, but I'm going to say 16 grams per mole. Which one of these substances, O2, N2, CO, HE, or CH4, which of those weighs 16 grams per mole? Make sure you get your final answer there. Hopefully this is going easy enough. I'm going to, let's see, 3 times equal to 3 times, yep, pinhole. So 12, 13, and 14 are all more examples of using the same math that we have been. So I'm going to give you the final answers. And what you need to do is show me your work on how I got these answers. For number 12, my final answer is 88 grams per mole. Number 13, my answer is 4.2 seconds. That was 13. Number 14, I'm getting 288 grams per mole. So these are my final answers. Your job is to show me how I got there. The last problem we will talk about more in another video, but just for right now, I'm going to give you the answer here. We'll talk about this more later, but neon is a gas that would deviate the least from the ideal gas law. Again, we'll explain this in the next video, but for right now, just circle neon so you have the assignment done.